Okay, let's give this a shot. I just actually recorded this a minute ago and everything went wrong. So one of the things I'd like to talk about today is unit conversions and axial transforms, because I found that this has been an issue on Piazza. And one of the reasons is that I think certain things are kind of missing, and I'd like to try and see if I can emphasize them in this video. So going forward from here, the learning objectives that I've set are, first of all, to look at what exactly I've seen in Piazza, what I'd kind of like to sort of make sure you strengthen as we head into the first quiz, particularly dealing with unit calculations and axial transforms, because I think that's one of the things that you'll find to be something very demanding and also very important in this course. You'll start to look, even when you go to the second half of the course, axial transforms follow you all the way through. So let's try a problem with units. And this problem is me going to the golf course. And the important thing here is that this fairway that I'm on is at a slight angle of alpha degrees. I chip the ball, and I'm trying to go a distance d, which is 8 feet away. And I hit the ball at an angle of beta with a velocity v sub naught. V sub naught is 16.3 feet per second. Beta is 43 degrees. Alpha is 2 degrees, so it's not a big slope. And the distance is 8 feet. Will I get the ball within 10 millimeters of the hole? And you can see this is a mashup of a lot of different units, 8 feet, feet per second, degrees, and millimeters. And so the first thing is I define an axial system that is parallel to the fairway. So the x-axis is in the same, is aligned with the grass, and y, which is normal. So if I take sort of those pieces and put them back in here, that's that xy coordinate system that I've just defined. There's, right here is that shot that I'm taking. Alpha is over here. And I'm going to define a second coordinate system, x1, y1. x1, y1 is just going to tell me what exactly the horizontal and vertical distances are. And that's more useful because I want to be able to write x1 double dot is equal to 0. If I use x double dot is not equal to 0 because it's at a small angle, but it's an angle. Y double dot is equal to minus g and is acting downwards. And it's actually y1, pardon me. x1 dot is just going to be the distance traveled, or the velocity of the ball, of the golf ball, and it's going to be at an angle alpha plus beta, so v naught cos alpha plus beta gives me x1 dot. y1 dot is going to be v naught sine alpha plus beta minus the acceleration of gravity, which is g. Finally, I have x1, which is equal to v naught cos alpha plus beta t. That's the distance horizontally that I'll travel along the x1 axis, not the x, because it's, again, slightly off. y1 is equal to v naught sine of alpha plus beta t minus 1/2 gt squared. So a standard projectile motion problem with the slight twist that it's at an angle with respect to the horizontal. Now, if I take this first x1 equation, I can get an expression that will tell me what t is. And if I do that, I can just find that it's x1 divided by v naught cos alpha plus beta. So from that, I can substitute it back into this other expression, v naught sine alpha plus beta t minus 1/2 gt squared, substitute it in for t, and I'll end up with y1 in terms of x1. y1 is tan alpha plus beta x1 minus g secant squared alpha plus beta divided by 2x1 squared. So I'll take that equation and I'm just going to leave it there. And the only reason I'm going to leave it there is so now I can start to solve the problem. Alpha plus beta, because this is a lecturer's problem, and the lecturer's problems often use 30, 45, 60 degrees, 0 and 90 of course also, works out really nicely. So what that does is it allows me to say tan alpha plus beta at 45 degrees is 1. secant squared alpha plus beta, hey, that's equal to 2. Nice numbers. And so if it's 2, the 2 here cancels, x1 squared's there, and there's a v naught squared that's missing. And substitute in terms, y equals x1 minus g x1 squared over v naught squared. For the ball to land, it's going to go up a small distance, and that's going to be x1 tan alpha is this distance, which is also y1. So x1 then is equal to v1 or v naught squared divided by g1 minus tan alpha. When I put all the numbers in, substitute all of this in, I'll get this result right here, just putting everything together. Combining, bringing the x1 to one side and then dividing that with everything. So let's do the calculation. I know I've got 16.3 for the velocity, 9.81 for gravity. I've got 2 degrees, so 1 minus 2, tan 2. And that's not a very satisfactory looking way to write this, because I get a number, and I'll get a number right away, but I have no idea where I'm getting it from. So it's bad form. Let's do this with units. And if I do it with unit, immediately what will stick out is the fact that I am mixing English and SI units. And when I do that, I see that my meters per second squared is going to be affected by feet per second, and I cannot cancel the terms out. So this is going to essentially be a result with feet squared per meter. So it will not be meters squared over meters. So this is not a good number or a good result. So again, bad form. So then what I do is I can immediately highlight and say, hey, I can correct this by just putting in 32.2 feet per second squared, which if you don't know what it is the standard acceleration for US customary English units. But if you don't want to sort of keep that in your head, just remember you can do the conversion between meters and feet. You get an x1, which is equal to 7.9668 feet. And now I am carrying this out to a ridiculous number of significant figures because I am not at a final result. And because I'm not at a final result, I don't want to sort of solve it yet this way. So finishing this problem, I know that I can hit a ball very, very professionally. 7.9668 feet. Now, of course, I can't hit it 9668 feet. Really, I'm going to say that 9.7 or 8 feet, really. If I divide that distance by cos alpha to get the distance I travel along, I'll get x1, dl, which is 7.97 feet. And when I do the separation, or the distance to the hole, which I was given as 8 feet, and I put in my 7.97 feet, I get minus 0.028 feet to the hole, which is minus 8.6 millimeters, which was what I was asked at the beginning. Is it less than 10 millimeters? Yep, that works out perfectly. And the only other thing is minus 0.34 inches, because really, if I were using English units, I'd be using it in inches at this point, because that's sort of the correct range for these kinds of values. When you include units in your calculations, errors become more apparent. And one of the things, again, this is something that people did in Piazza. It's very normal to do this, but as you're writing your calculations, try to put your units in. And when you do that, you'll find that it's a lot easier to identify potential errors. Second one is axial transforms. Lots of questions about this also. Plane starts its descent into the airport. It's a distance, and I'm actually going to scratch out the r naughts here and the theta naughts. I'm just going to call it r. Theta r is equal to 37 kilometers. Theta is equal to something. Height is 2,500 meters. You're given that the velocity of the plane starts out at 2 kilometers per minute. Velocity in y is minus 100 meters per minute. And acceleration x is equal to minus 5.1 meters per second squared. You can see I'm going a little bit wild in terms of putting in values here for units that really I would never do normally. I'd put this in kilometers per hour, meters per second squared. I wouldn't do, and I would have it in meters, even if for the 37 kilometers. So having done that, I want to find r dot, theta dot, r double dot, and theta double dot. So let's define a coordinate system, x and y. Again, good standard starting point for all of these problems. Draw out your coordinate system, draw the picture. When you draw the picture, you get more confident in what you're doing here. Distance between the plane and the radar is given by 37 kilometers, and that theta is not yet given, but we know what it is. You got an H, you got an R, you can figure it out. It's a right triangle. I'm going to define a coordinate system unit vector, which is I and j, which is the standard direction in the positive to the right and positive vertical. And of course, I have the definition of velocity, and velocity is going to be x dot in the I direction, y dot in the j direction. Acceleration, x double dot in the I direction, y double dot in the j direction. Putting that all together, I can say y dot equals minus 10 meters per second, which I did the conversion. I'm not going to bother you with this. I actually encourage you as you do these problems, and that you do these problems. I chose these problems because I think it's good to do them. 33.3 meters per second. X dot is equal to v naught squared minus y dot squared. And you're given v naught is 2 kilometers per minute. So you well, and it's 33.3 meters per second here. X dot ends up being minus 31.8 meters per second. X double dot is given to you as actually minus, it's a negative, it's decreasing, 5.1 meters per second squared, and y double dot is equal to 0. So I'm going to define on here my other coordinate, ER, or unit vectors, ER and E theta, and you can see them there, and I have them on this. Now, of course, these are not unit vectors because they're really long compared to I and j, but bear with me, I'm drawing this by hand. I can also say that v is equal to r dot e sub r plus r theta dot e sub theta, and acceleration is r double dot minus r theta dot squared er plus r theta double dot plus twice r dot theta dot in the e theta direction. All of this is just to say, hey, by the way, these are the standard definitions. These are in the crib sheet that I've talked about in lecture, and I suspect other lecturers have also, but it's in the module crib sheet. These definitions are important, and if you choose to make your own crib sheet, and I do encourage you to do that because it's a very helpful way to study this course, you're going to find that it's helpful to sort of understand this material. So I put numbers in, I put these relationships, and now I can sort of solve through everything. So let's look at the I vector. The I vector is going to be made up of an ER and a minus E theta, and that's a theta here. And so it's ER cos theta, and it's minus E theta sine theta. Now you'll notice that this is negative because the positive direction is going to be up and to the left. So in order for this vector to actually fill in the rest of the I vector, it has to be a negative value. So I end up with I vector is ER cos theta minus E theta sine theta. If we look at J, we can do the same thing, but now ER is positive, E theta is positive. Both of them are at an angle theta, and this is an angle theta up here. Put in the terms, and I get J is equal to ER sine theta plus E theta cos theta. So again, nice sort of result here. Everything kind of makes sense, and I've got something to work from here. Substituting into the equations, I get V is equal to x dot cos theta plus y dot sine theta ER minus x dot sine theta plus y dot cos theta E theta. So now I have both of the terms. I have all of the expressions here. Same thing for acceleration, which is x double dot cos theta plus y double dot sine theta in the ER direction minus x double dot sine theta plus y double dot cos theta E theta. So previously we had found, or we didn't really find it, we just sort of knew from definition that velocity is equal to r dot er, r theta dot e theta. That's standard definition. You don't have to rederive this each time, you just use it. R double dot minus r theta dot squared er, r double theta double dot plus twice r dot theta dot e theta. Again, you don't have to rederive them, you have to know what they are. You have to recognize here, and I'm just going to be a bit pedantic, this is AR, and this is A theta. Same thing. Now, we just found out what the terms are for the x and y components of acceleration and velocity in the ER and E theta direction. So it can substitute those back, and I can write those as V and A. So the terms in orange and green correspond to each other. The terms in dark green and dark blue correspond to each other. So if we do the substitution, we find that r dot equals x dot cos theta plus y dot sine theta. Theta dot equals minus x sine theta, x dot sine theta plus y dot cos theta divided by r. R double dot is equal to x double dot cos theta plus y double dot sine theta plus r theta dot squared. Theta double dot is equal to minus x double dot sine theta y double dot cos theta minus 2 r dot theta dot divided by r. Now you can see right away that you have all these terms. Everything sort of is just taking the definitions and taking the two different geometries. But the fundamental point here is that in both of these cases, nothing has changed. V is equal to V. It's just that it's made up of different components. A is equal to A. Again, made up of different components. Substituting in values, you get negative 33.3 meters per second. Theta dot is equal to 1.59 times 10 to the minus 5 rads per second. R double dot is equal to minus 5.1 meters per second squared. Theta double dot is 9.35 times 10 to the minus 6 rads per second squared. Honestly, in this problem, it's basically straight line motion because they're not changing very much yet. I'd probably have to do one which is closer to the radar to make that happen. But the important point here is that you can do these substitutions, you get these results, and you understand them because you've drawn the figures. Once you draw the figures, include your units, everything works out. I tend to present these examples often with variables all the way through. That is actually a really good way to do it because you don't get confused about where your numbers are coming from. However, it does get very bulky, and you can see in some of the lectures that I do that I end up with terms with ridiculous numbers of variables that if I were doing it on my own, I'd organize things a little bit, but I would make sure that I would cover it so that it's correct all the way through. So again, unit calculations, variables as far as you can without losing sight of what the problem is. So in terms of conclusions, please write your units, draw your figures, and carefully look at your axes. You have ample examples available to you. Please take advantage of them as much as you can. And as soon as you can, try to take a look at what's available in the notes. I mean, all of the lecturers have put out their notes. All of the lecturers have put some really interesting examples out. And we also have old exams, old quizzes, and the tutorials there to help you. Thank you very much, and we'll talk again.